and all of them must at least have the counts associated with the value j, right? I never decremented anything, and every counter has at least the right count. It may also have collisions, right? But it doesn't. It always has at least the right count. So no counter is an overestimate. So that's why it's okay. I want to take the minimum. If they're all overestimates, then my best of these estimates is the smallest of them. Because I know they can't be too small, so I might as well take the smallest of them, and that'll be the best estimate. So does that make sense? Okay, so now, why do I get this upper bound? Why can this not be too big? I think, technically I needed a 2 epsilon. Why can it not be too big? So, the kind of basic idea is to look at I won't be able to get all the way through this analysis, but we're going to look at just one of these rows and look at the expected overcount. Okay? We're going to look at the expected overcount of one of the rows. And so that's the probability that I have a collision. Right? So I'm going to say Yij is going to be the so let's see, it's going to be f of, let's call this, so this is going to be for row I. Let's just call this yx. It's going to be f of x if, and this is force some j in n here, right? So it's f of x if the hash function I that I care about at x is equal to the hash function for j. And it's going to be 0 otherwise. Okay, so this is a random variable for some other element x. So this is for some x in n. Right? So I can look at the frequency of x, and it's going to be equal to, it's going to be, I get that frequency as an overcount here, only if it collides. So that means it goes to the same location as the j that I care about. So there's a collision. Okay, so what is the probability of having a collision? The probability of a collision, so the probability of Hix equals Hij, let's say for x not equal to j, this should be equal to 1 over k, right? They should be all these locations are equally likely, right? So now the expected value of Yx is going to be 1 over k times f of x. 1 over k. So I hit this condition 1 out of k times, and this condition the rest of the time. And this condition contributes 0, so I have 1 out of k times f of x. So now if I look at, because now I can look at the expected value of the sum over x in a not equal to j of yx. But if I look at the sum of all possible elements, sorry, not in n, if I sum of all these possible elements, this is going to be equal to the sum of x in n not equal to j of 1 over k times f of x. And so if I factor out the 1 over k, what is the sum of all these counts? The sum of all these counts, this is going to be less than 1 over k times m. Because m is all the counts, including the count of j. So even if I include the count of j in this, I still get m here, right? So the expected overcount is going to be m over k. And m over k was roughly this value here, right? So this is, I said it was less than this with some large probability, but this is the expected overcount of one of these rows. Okay? So I can say the expected overcount is m over k, which is what I want. Now, I've run out of time. Now, by using these s different rows, you can drive the probability down to this 1 minus delta. Okay? So this you can do using, you can use a Chernoff bound, but you just need the Markov inequality, which is much simpler version. And so that's how you're able to get this one. So this is a much cooler algorithm. The advantage is that you can subtract things using this algorithm. You can see an element in the stream say, oh yeah, that thing I saw before, I'm actually subtracting. Or if it's often called the turnstile model, you're keeping track of people going to a stadium. You can keep track when they go out to. And then this bound is in terms of the number of people left at the end. So if you subtract, you can do with this algorithm. The Misha-Gries algorithm cannot do subtractions. So that's kind of one of the really big advantages of this, even though it needs some extra space. Okay.